So if the gate is of multiple stages or multiple levels, then what is the delay? Delay would depend on the longest path from input to output. Again, the assumption is that all the inputs are available at same time. If all the inputs will change at same time or are available at same time, then we can find out what is the longest path. So this longest path is also called critical path. This critical path would define the delay. So it even in two logic level implementation, this particular definition can work. So whatever is the longest path. So in two level logic optimization, if at first level a particular gate has more number of input, so that will form the critical path. That would be part of critical path. So here we see that, let's say this is the logic implementation we have done. So in this logic implementation, this is the shortest path, because whenever this D input is available, after that there is only one gate delay to change the output. However, if any of these inputs A or B will change, then first N1 will change, then N2 will change, then Y will change. So this become the critical path. And again, as I said before, so this, if we have different paths, so some paths are short paths, some paths are much larger in delay, so that would also means that in this Y output there would be more number of glitches. This Y would keep on transitioning from 0 to 1, 1 to 0 before it will get stabilized to the final output. Okay, so with let's see that now if these delays are there and we are using Verilog for modeling of this gate level implementation, if we want to represent these delays in Verilog implementation, how do we do? So there are two kind of modeling we have studied in our previous lecture of Verilog. So we have seen structural modeling and data flow modeling. In structural modeling, the modeling is done using basic gates, AND gate, OR gate, NOT gate. If we tell that what is the delay of that particular AND gate, OR gate or NOT gate, that is sufficient. So if the delay of all the basic gates are known, then whatever is built using that gate. So let's say in our previous assignment we have designed XOR gate. So from the XOR gate, let's say we even create something else, that delay would be imparted, delay would be introduced in the XOR gate, and the same delay could be propagated. So the other logic which would be implemented using that XOR gate will also have those delay characteristics. So what I mean to say here, I would rephrase this as that if I want to model delay in my structural modeling, in my leaf level design, wherever AND gate, OR gate, NOT gate or basic gates are instantiated, then I should write my delay statements there. I should tell that what would be the delay of this particular AND gate. So here I wanted to say that delay of my AND gate is 5 units. You remember that this AND is the gate declaration, and this is the instance name. A1 is the A1 instance of my AND gate, and this #5 essentially means that whenever input I1 and I2 will change, after 5 units of time my out will change. This delay is also written as sometimes two values, like in the parenthesis we write two values. So first value represent the rise time, the second value represent the fall time. So rise time means the output. If output is changing from 0 to 1, then this would be the delay. If output is changing from 1 to 0, then this would be the delay. So as I said initially in the starting of this lecture, that my output delay change, it depends on the transition, whether the transition is from 1 to 0 or 0 to 1. So that particular thing can also be modeled using Verilog. There could be third parameter to delay also, that is rise time, fall time and switch off time. So In switch off time is a special like which we have not considered so far. So if delay is if the output is neither high nor low, but it is at a high impedance, or it's disconnected, or it was switch off. So from switch off, how much time it will take to go into state of 0 or state of 1, that is called switch off time. So in most of our implementation, to make it simple, we only consider one delay, but if we want to model more number of things, then these delays are also considered. Okay, so this is when out of these three input, one of the input is not specified, only two inputs are specified, it automatically take it as a rise time and fall time. When only one input is specified, that means the delay is fixed for all the cases. So it essentially means that for rise time also delay would be 5, for fall time also delay would be 5, for switch off time also delay would be 5. Okay, in case of there is no specification of hash, it means that there is no delay, or we can also call it zero delay. In case of data flow modeling, there are two ways of specifying delay. One, that whenever we do assign, whenever there is a assign statement, after assign statement we can write hash 10 or hash whatever time. So after that much amount of time, this input change would be reflected in the output. Okay, so this means that this is also an inertial delay or propagation delay, that whenever input changes would be there, the output would change after that much amount of time. So there is one small caveat here, that if my input changes, let's say input changed at 0 time, and after that input again changed at time 8, then there is a possibility that there is no transition at output, because to make it certain, although we said in hardware things are uncertain, but Verilog being a deterministic language, here we have a very clear cut rules that if there is another change in the input, then this hash 10 may not apply. So because my input has further changed before the delay of this particular transition, so it would depend on the what is the impact of this after before this completion of delay of this transition. Okay, so in other words, we have to say that to make it correct, my input delay should not change before the delay of the transition, or before the propagation delay. Okay, and there is also a possibility of a propagation delay because of wires. So we can say here we can also define a propagation delay on wires. So that means whenever we define this out as a wire, we can also say hash 10, which means that whenever anything is assigned to out, there would be a delay of 10. So these two statements are slightly different. In the first statement, we are saying that this expression would be computed, and that computation would be given after a certain time to my output. Okay, so this expression we can use for delay in the in calculating any kind of operations. Okay, here it's a logical AND operation, so logical AND or NOT or XOR. So all those operations delay we can use this using this data flow modeling. But there are some delays because of just wires. So there could be simple assign statement. Let's say in1 equal to out. So if we use this particular statement, that any assignment to out will again lead to a delay of 10. So sometimes this is required because some wires will have propagation delay, because those wires are long wires, and because although voltage and current can reach at instantaneous time, but in VLSI or in these chips, the chips are also very small, incredibly small. if the distance is in the terms of nanometer or hundreds of nanometers, then also the delay of those wires could be there. So because of that, we also consider the propagation delay of wires, and that's why Verilog also model it. So this is how those delays can be modeled in Verilog, so that we can see the overall functionality in terms of delay for a particular circuit. So this was about the delay. So there are a couple of small topics which I would like to cover. So so far we have seen f expression, any particular expression or any particular function usually have a single input, single output. So there are multiple inputs, but there is a single output. So there is also additional possibility that the same inputs, there could be multiple functions. So here I am taking some example that a, b, c, d are the inputs, but there are 4 different functions: f1, f2, f3, f4. All of these functions are represented in canonical sum of mean terms. Now when I am designing them, will there be any impact, or how should I design? As far as designing is concerned or implementation is concerned, so we, all these functions f1, f2, f3, f4, we would develop, or we would put independent k maps for all of them, and after independent solving of k maps, we will write this f1, f2, f3, f4 as a independent sum of product expressions, or independent 2-level logic. So even though there are multiple output, it does not matter from the implementation perspective or from the design perspective if we are using 2-level implementations. However, to save area, what we can do sometime, that let's say some particular product term has appeared in function 1 as well as in function 2. So because same product term is there in function 1 and function 2, so we can reuse that particular sum term, product term, and if we reuse that product term, so that means some area could be minimized. So that essentially means that if multiple output functions are there, they give us certain opportunity to reduce the area, so we can find out if there is some common product terms, or if there are some common sum terms. Those common sum terms can be utilized to reduce the area. So what would be the impact? There would be the fan out of that particular gate would increase. So let's say there is a common product term which is there in this function as well as this function. So that means that product term we can instantiate once, but the output has to go to f1 as well as f2. So the fan out of that particular gate would increase. But effectively it's a good optimization, because we are reducing the area with a slight increase in the delay. Delay would increase because otherwise fan out has to be 1, but now fan out is 2. Okay, so however, so one more small topic we would like to cover, that what is the complexity of a Kuhn-McCleskey method. So this or optimization, what is the complexity of the Boolean optimizations which we have done. And so how we were doing Boolean optimization? So first we were constructing, we given an expression, first we were constructing in the terms of sum of mean terms or sum of max terms. So that means we were representing our function in a canonical form, and given n variables, if the number of variables are n, then what is the possibility, how many mean terms or how many max terms would be there? That the maximum possibility of n terms, mean terms, could be 2 to the power n minus 1. So for example, for n equal to 4, there could be 15 mean terms which are possible. Okay, so even though the total number of mean terms may not be 2 to the power n, but it could be of the order of 2 to the power n. So let's say we have so far we have solved multiple of the examples where number of mean terms, if the number of variables are 4, is in the range of 8, 9, 10, 11. So that means it's of the order, it's nearby that 2 to the power n minus 1 range. Now, if we follow closely how this Quine-McCleskey method is working, so this QM method is working by comparing each mean term with the other mean term to find that if there is a one variable difference or not. So that means the comparisons are also of the order of 2 to the power n. It's not only 2 to the power n. So your ideally you would like to compare each of this mean term 2 to the power n mean term with the other 2 to the power n mean terms. The total number of comparisons would be 2 to the power 2n in that case. But as we have seen in our previous lecture, we are doing grouping so that the number of comparisons could be minimized. But still, our observation was that the number of comparisons are still more than 2 to the power n. So whatever were the number of mean terms, the number of comparisons were still much more than that. So this first stage of prime implicants, where the number of stages are also of the order of n minus 1, capital N minus 1. So first we are reducing one variable, then the second variable, then the third variable. So the number of stages are also of the order of n, and in each stage the number of comparisons are exponential. So total number of comparisons are kind of non-polynomial. Okay, so some theoreticians have given the total number of or maximum number of prime implicants given the number of variables n is equal to 3 to the power n divided by n. So that means the total number of prime implicants which could be there is the power of n. Okay, so and n is a variable. Similarly, in the second phase, covering is also an iterative process. So we first have removed the essential prime implicants by saying that these are the implicants which are covered by only mean terms which are covered by only few implicants, or only one implicant, that become essential prime implicant, gone. And after that, remaining prime implicants we are still covering mean term one by one, and total number of mean terms are exponential. So the overall cost of this QM method is non-polynomial. What it means that non-polynomial, what is the polynomial polynomial complexity? Polynomial means your complexity is the power of n is power 2, n is power 3, n is power 4, n is power x, where x is a degree. But if the complexity is equal to 3 to the power n here, so that means it would exponentially increase if n will increase, which essentially means that if the number of variables in the logic minimization is of the order of 3, 4, 5, 6, we would be able to find an optimal solution using K-map or Quine-McCleskey method. But if the number of variables grows beyond a certain number, let's say beyond 10, whatever computational power we have today, it won't be sufficient to find an optimal solution. If optimal solution is not there, what will we do? We will try to find non-optimal solution or an approximate solution which is also close to optimal solution, not very bad but still okay. Why we will resort to this approximate solution? Because optimal solution will take exponential amount of time, and that exponential amount of time is not worth. So let's say I have some 10 or 12 variables. Because of those 10 or 12 variables, my machine is occupied for whole day, and in the end I may find an optimal solution which has one literal less than the non-optimal solution. It's not worth, correct? So that's why we find a trade-off. We say that non-optimal solutions are also okay if the number of variables are very, very large, because the optimal solution is exponential in nature, non-polynomial in nature, and these NP type of problems, the amount of time it takes, that's why we have to resort to some kind of a approximate solution. And how do we calculate this approximate solution? This will come from the algebra. So in the algebra, we have seen that in our previous module, we have seen there were a couple of stages that we were trying to remove redundant terms, try to add some terms and then remove some terms, try to remove variables, try to remove literals. So all those logic expressions would be done one by one. All these logic expressions would be done one by one and iteratively, so that we reach near an optimal solution. If we reach at a solution which from where we see that no further cost can be reduced, then we settle out for that particular solution. Okay, so now because Quine-McCleskey is not an optimal, will not be able to give optimal solution in a real time for large number of variables, we also look for other methods. Okay, so now we see that so we have seen in this particular lecture that sometime we go for a 2-level optimization, sometime we are going for a multiple level optimization. So if number of inputs are large, that also lead us to suggest that you shouldn't go for 2-level optimization, but you should go for a multiple level optimization, because final implementation would require a gate which has a smaller fan-in. So then this also gives us another question, that why not to design an optimization or design a final circuit which has a multiple level optimization, starting from the scratch, starting from whenever we have started optimizing, why not to go for multiple level optimization? So the reason for that is that we don't go for multiple level optimizations because even 2-level optimization problem is hard, computationally hard. It is non-polynomial in nature, although known methods exist for optimal results. Okay, in multiple level optimizations, there is no known method for giving optimal results. Okay, so because there is no known method, but so that's why keeping multiple level optimization as a goal is not usually done. Multiple level optimization is done as a side effect. So whenever we see large number of inputs, then we try to do multiple level realization, and whenever multiple output function is there, then also we try to see that if there is some common factors are there between two functions, so that we can optimize on delay, optimize on area. So this multiple level optimization is usually the side effect. So we start with 2-level optimization. After we are done with 2-level optimization, then to finally go for a circuit implementation, it's usually it is done by software, it's done by tool itself. We don't go for manual multiple level optimizations, but yes, for example, this Verilog compiler, when it will implement the circuit, then it will go for multiple level optimization wherever it see that 2-level optimization is not optimal, or area or delay will not be optimal there, so it will break it into multiple levels, and then it will also try to see what other factors can be brought out, so that we can further take the best advantage of multiple level optimization. So with this we close this particular module, and I would like to summarize that in this particular module we have seen what is a Boolean function, how do we represent it using various different forms. We can represent it using truth table, we can represent it using Boolean expressions, and we have also seen that 2 Boolean expression could also be equivalent, and we have also seen various laws of Boolean algebra. We have seen that these laws are slightly different from our regular algebra, but are interesting because they can help us in much more optimizations. After understanding these Boolean functions and Boolean algebra, then we have seen that how we can optimize a Boolean expression, how we can reduce the number of product terms, number of sum terms, or number of literals. We have seen that we can use that either using algebra or using a graphical representation like K-map or a tabular representation like QM method. All of these methods were good, and they were essentially using the same basic functions, same basic criteria, same algebraic simplifications. But K-map and QM are more systematic because we know that they will give a certain optimal solution. After that, we have also seen how these expressions or optimal expressions, how they would be implemented using gates. We have seen different kind of gates: and, or, zor, XNOR, not. So all these gates we have seen, what are their characteristics, how we can convert AND gate into a NAND gate, NAND gate into a AND gate, and OR gate. So those transformations we have seen. We have also seen their delay characteristics. What is the meaning of a propagation delay? Along with that, we have also seen how to write a basic Verilog program. So one thing which is missing in this whole story, we don't know from where these Boolean equations or Boolean expressions are coming. Who is giving you these Boolean expression to optimize? Of course, you can say your faculty, your instructor is saying that optimize this particular expression, but how these expressions came into his mind, or basically who is creating those Boolean functions? What is the meaning of those Boolean functions? So all this particular question we will start answering in our next module. So till then, thank you very much. Have a good day.